In this video we're going to look at a constrained optimization problem. We have a rectangular building that's to cover 20,000 square feet. Now zoning regulations say that there must be 20 feet of space both in front and back of the building for entrances, loading docks, and other miscellaneous structures. They also require 10 feet of space on each side of the building. So we want to find the dimensions of the smallest piece of property which can fit the 20,000 square foot rectangular building. So first thing in a problem like this is probably best to get an idea of what's going on through a picture. So first off, let's say here's the building. Now we know the building has to be 20,000 square feet. And we don't know its dimensions, so perhaps that's what we label our variables. So maybe x and y. So we know that x times y must be 20,000. And there's our constraint. Now we're going to have to put structures. Let's call this the front and this the back. You can do it either way. But we know that zoning laws are what are requiring this extra space. 20 feet of space in back and 10 on the sides. So we get this larger piece of property here, and that's the one we have to find the dimensions of. So that's the one we're trying to minimize. So here, from here to here, we know it's y, and then we're adding 10 here and 10 here. So this whole length would be y plus 20. Similarly, over here we're adding 20 to x on both places, and so this would be x plus 40. So that's going to give us the area that we're trying to minimize, because we have area equals x plus 40 times y plus 20. So let's move this so we have some room now that we have everything set up. So our area, let's go ahead and multiply this out. It might make it a little easier to work with, maybe not. Let's just see what it is. We got x times y plus 40y plus 20x plus 800. So that comes from just foiling everything out in there. And now the issue is we have a function in terms of two variables. Now I'm going to solve this in terms of Calc 1 in this video, but I'll do another video in which I use Lagrange multipliers to do this problem if you want to check that out. What I need to do is solve this equation for one of my variables, my constraint. Let's solve it for y. So we know y equals 20,000 over x. And I'm going to plug that in for my y's. So I have a equals x times 20,000 over x plus 40 times 20,000 over x plus 20x, that stays the same, plus 800. Okay, those x's will cancel, so we can go ahead and cancel those, and we're going to be able to do some multiplying there. So we have 800,000 over x, so that comes from that term. I'm going to add the 20,000 and the 800 together at the end, plus 20x plus 20,800. So that's my area. Now we need to see if there's any critical points. So we're going to take the derivative, we'll call it a prime, and set it to 0. Now here, this is the same as 800,000 times x to the negative 1. So pull the negative 1 out front, so negative 800,000, and increase the power by 1, so that becomes over x squared, plus 20, and we plus, well, this is just a constant, so it goes away. So checking for critical points, I'm going to set this to 0. And what I'm going to do is I'm going to add this across. So I'm going to add 800,000 over x squared to both sides. So I'm going to end up with 20 equals 800,000, that's a comma, over x squared. And now I can cross multiply the x squared. So coming up here, I got 20 x squared equals 800,000. Dividing both sides by 20, I've got x squared equals 40,000. Square root both sides. I've got a critical point at x equals 200. So that's one of my critical points. That's my only critical point. So the only other thing we need to check are the endpoints. So x has to be between 0 and 20,000, because otherwise we won't have any kind of rectangle. So 200 is going to be a max or a min. There's a couple different ways we could check that. One would be by doing the second derivative test. So if I find my a double prime, this constant's going to go away. The derivative of this, I pull the negative 2 down, and I've got then 1,600,000 over x cubed. Now the way the second derivative test works, well, you plug in your critical value into the second derivative, and if I plug in 200, I get a positive number. I'm not worried what the number is, it's positive. Remember, when the second derivative is positive, that means our function's concave up, so our critical point must sit at the bottom, so we have a min. So our min's going to happen when x is 200. To solve for y, we already have y in terms of x, so 200,000 over 200 equals 100. And so there's the x and the y that give the minimum amount of space we're going to need. Now that's not the dimensions of the plot of land, because remember, we still have to add the zoning requirements. So to x we had to add 40. So the minimum was going to be 240 feet by, you have to have 20 to y, 120 feet. So there's our minimum space. Like I said, I'll do this problem with Lagrange multipliers for those of you who are interested in a separate video.